The Moon, Earth's only natural satellite, orbits our planet at a distance that has fascinated scientists and casual observers alike for millennia. While we often hear a single figure quoted, the reality is more complex than a static measurement can convey. The commonly accepted average distance between Earth and the Moon is approximately 384,400 kilometers, 238,255 miles. This measurement serves as a useful reference point, but it represents only the middle value in a continually changing relationship between our planet and its celestial companion. The Moon's orbit follows an elliptical path rather than a perfect circle, resulting in varying distances throughout each lunar cycle that have measurable effects on both the Moon's appearance and its gravitational influence on Earth. The Moon's orbit around Earth is not circular but elliptical, with Earth positioned at one of the foci rather than at the center of the ellipse. Astronomers quantify how much an orbit deviates from a perfect circle using a value called eccentricity, with 0 representing a perfect circle and values approaching 1 indicating increasingly elongated ellipses. The Moon's orbit has an eccentricity of 0.05, which is relatively modest compared to some planetary orbits, but sufficient to create significant distance variations. For context, Venus has the most circular orbit in our solar system with an eccentricity of merely 0.007, while Mercury has the most eccentric planetary orbit at 0.2. This elliptical path brings the Moon to its closest point to Earth, called perigee, at approximately 356,470 kilometers, 221,500 miles. At this position, the Moon exerts its strongest gravitational pull on Earth, contributing to higher ocean tides and appearing larger in the night sky. Conversely, at its most distant point, known as apogee, the Moon recedes to approximately 405,696 kilometers, 252,088 miles, from our planet. The difference of nearly 50,000 kilometers between perigee and apogee represents a variation of about 13% in the Earth-Moon distance throughout each orbital cycle. To put this vast distance in perspective, at apogee, the separation between Earth and the Moon is so great that all 7 other planets in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, could theoretically fit within this gap if placed end to end. The combined average diameters of these planets total approximately 380,016 kilometers, 236,100 miles, illustrating the considerable scale of the Earth-Moon system within our solar neighborhood. Humanity's quest to determine the lunar distance dates back to ancient civilizations. In the 2nd century BCE, the Greek astronomer Hipparchus pioneered lunar distance measurement using parallax techniques. By observing the Moon from different locations on Earth and measuring the slight change in its apparent position against the background stars, Hipparchus calculated values for both the minimum and maximum distances between Earth and Moon that were surprisingly close to modern measurements. This remarkable achievement demonstrates the ingenuity of ancient astronomical methods despite limited technology. For centuries, the accuracy of lunar distance measurements remained constrained by uncertain knowledge of Earth's own dimensions. Since calculating absolute distances required understanding Earth's size, ambiguities in terrestrial measurements directly affected lunar distance calculations. Eratosthenes had attempted to measure Earth's circumference in the 3rd century BCE, but confusion over the exact length of his unit of measurement created persistent uncertainties. Even during Newton's time in the 17th century, there remained significant imprecision in Earth's measured dimensions, limiting the accuracy of lunar distance calculations until more reliable terrestrial measurements became available. Today's highly precise measurements of lunar distance rely primarily on technology developed during the space age. The most accurate method emerged from the Apollo program when astronauts placed retroreflectors, specialized mirror arrays, on the lunar surface during the Apollo 11, 14, and 15 missions. These reflectors enable scientists to conduct lunar laser ranging experiments, in which short pulses of laser light are directed at the Moon from Earth-based observatories. By precisely measuring the time required for the light to travel to the Moon, reflect off the retroreflectors, and return to Earth, scientists can calculate the exact distance with unprecedented accuracy. This technique has achieved millimeter-level precision in determining the Earth-Moon distance. Before laser ranging became available, radar technology provided improved measurements beginning in the mid-20th century. In 1957, the U.S. Naval Research Laboratory attempted to determine lunar distance by broadcasting radar pulses toward the moon and measuring the time required for the echoes to return. However, these early attempts suffered from high signal noise that compromised reliability. The following year, the Royal Radar Establishment in England refined the method using longer pulse durations, achieving more consistent results. While not as precise as modern laser ranging, these radar experiments represented a significant advancement over earlier optical methods. The varying distance between Earth and Moon produces several noticeable effects. When the Moon is at perigee, it appears approximately 14% larger in diameter and shines 30% brighter compared to when it is at apogee. These visual differences have given rise to popular terminology such as supermoon for a full moon occurring near perigee and micromoon for one occurring near apogee. Media attention to these phenomena has increased public awareness of the Moon's orbital dynamics and the changing Earth-Moon distance. Another way to conceptualize the Moon's distance relates to light travel time. Light travels at approximately 300,000 kilometers per second, meaning it takes about 1.3 seconds for light to travel from the Moon back to Earth. Astronomers sometimes express this by saying the Moon is 1.3 light seconds away. This perspective helps illustrate why lunar laser ranging experiments require precise timing measurements. Even the slightest error in timing would result in significant distance calculation inaccuracies. The Moon's orbit is not static, but evolves over time due to complex gravitational interactions. The Moon's velocity around Earth varies considerably throughout its orbit, ranging from approximately 3,470 kilometers per hour to 3,973 kilometers per hour, with an average velocity of about 3,682.8 kilometers per hour, or 1.023 kilometers per second. This variation in speed is a direct consequence of the elliptical nature of the orbit, as the Moon accelerates when approaching perigee and decelerates when approaching apogee. One of the most significant long-term changes in the Earth-Moon relationship is the gradual increase in the average distance between the two bodies. Through a process driven primarily by tidal forces, the Moon is slowly receding from Earth. Ocean tides caused by lunar gravity create friction that transfers rotational energy from Earth to the Moon's orbit. Rather than causing the Moon to speed up, this additional energy actually causes the Moon to slow down and move to a higher orbit. This gradual recession has been precisely measured using the lunar laser ranging experiments, confirming that the Moon is moving away from Earth at a rate of approximately 3.8 centimeters per year. The distance between Earth and the Moon represents a dynamic relationship rather than a fixed measurement. From its average value of 384,400 kilometers to the variations between perigee and apogee, this distance affects numerous phenomena observable from Earth and has implications for space exploration, tidal patterns, and our understanding of the Earth-Moon system's evolution. The journey to accurately measure lunar distance spans from ancient astronomers using geometric principles to modern scientists employing laser technology with millimeter precision. As our closest celestial neighbor, the Moon continues to serve as humanity's first stepping stone into the solar system, with its varying distance representing both a challenge and an opportunity for ongoing scientific discovery and space exploration endeavors.